we are happy to have the 8th lecture by Professor Ravin Bhatt, and he would be talking about MBL and in the quantum Hall regime. So, yeah.
Hey, welcome to the last lecture in this series. And we're finally coming to quantum Hall regime with interacting electrons as opposed to non-interacting electrons, which is what we covered in the previous lecture on Tuesday. When you have actual electrons with interactions, the quantum Hall phase diagram, which is shown here on the left, which is reproduced by non-interacting electrons in a disordered material with some weak disorder, not very strong disorder, goes into this much more complicated phase diagram when you put in electron-electron interaction. So the actual, as you make the sample cleaner and cleaner, what turns out to be this set of steps develops smaller steps in between, and these spikes in the longitudinal resistance grow in number and start having a very interesting structure. So we're going to study that today. So basically the outline of today's talk is I'm going to first try and sort of put the entire lecture series in context by talking why did I call this from single particle to many body localization. And I will start again with Anderson localization, then which is localization of single electrons or single particles with no interactions, then localizations of spins at low energy, which was done some 20 years later. And then one big breakthrough came in 2005, 2006, when the concept of many body localization was introduced in a perturbative way by Basco, Lehner, and Altshuler. And then I will go to some actual numerical work on the random transverse field spin half chain, which showed that in this particular model, you can actually have a phase transition from an ergodic phase to a many body localized phase. Then I will go back to the quantum Hall problem, because all of that has nothing to do with quantum Hall physics, but we are going to study many body localization and interactions in the quantum Hall context. So I'll just very briefly summarize this very rich phase diagram that I showed you in the previous slide, and then talk about one thing that you can do when you disorder such a system, which is you can have a transition from a fractional quantum Hall phase, which is a topological phase, to an Anderson insulator. It's a transition in the ground state of the system. So that's still not much to do with many body localization. But then we will finally talk about many body localization in the quantum Hall context. I will talk about eigenvalue spacing statistics. I will talk about a couple of attempts at trying to understand that. And we will do two different models in addition to the Landau level model. We'll split the Landau level into subbands and see how things change. And then we will also talk about an impurity band and the Landau level coming out of the Landau level. And we will study in particular eigenvalue spacing statistics, which is a characteristic of localized versus extended eigenstates. And finally, I will talk about one attempt at trying to understand many body localizations by studying the dynamics of this disordered system. And then finally, try and summarize all the conclusions of these last few lectures. So again, the beginning of the story starts with Anderson's paper in 1958, or it was actually submitted in 57, accepted in 58, which consists of a tight binding lattice in which, in his case, he just considered a three-dimensional cubic tight binding lattice with nearest neighbor hopping and disordered energies, on-site energies, which were drawn randomly from this uniform distribution between minus W/2 and plus W/2. And what happens as you increase this quantity W, for W equal to 0, the density of states is very well understood. It's just it has its Van Hoff singularities, band edges at minus 6V and plus 6V. As you increase W, you find that you develop tails in the densities of states, but still most of the eigenstates in the middle of the band are extended. It's only in the tail that you get some localized states. In this particular case, it also turns out that even at the band edge, the states start getting delocalized again. So that's a reentrant behavior here, which I haven't shown, but that's specifically because of this sharp cutoff here. And then at large values of disorder, the whole band is expected to localize. And this is basically the phenomenon of Anderson localization. And it's a single particle problem. Okay. And here I show the phase diagram as computed by McKinnon and Kramer for different kinds of disorder. The box distribution is the one that was considered by Anderson. They also considered Gaussian and Lorentzian distributions. And basically what they found was the center for small energies and disorder less than a critical value, you have extended states, and outside this region, above that, and on to the right of this, you have localized states. And you can study this, and we went through that in one of the early lectures. So actually, Anderson was trying to study spin localization, but he instead did the single particle problem. And but many years later, Patrick Lee and I realized that in fact, if you take dopants in semiconductors, because of the broad distribution of exchanges between them, the low-lying states of such a system, spin excitations, are actually localized on a few sites. And in this, I went through this large disorder renormalization scheme and showed that basically at very low energies, what you're doing is you're basically making a singlet to triplet transition. That's the excitation. And they are on basically two sites. Most of the amplitude is on two sites. And this gets better and better as you go to lower energies. And we also showed later, about a decade later, that with Daniel Fisher, that even the metallic phase has localized spins. So spin localization exists for large disorder. So that certainly at low energies. Okay, this is all low energy physics that I'm talking about. On the other hand, the real question was, how do you characterize many-body eigenstates and localization of many-body eigenstates? And there the crucial advance was made by Basco, Lehner, and Altschuler in a paper that is very long. In fact, Annals of Physics was one of the few journals that accepted it, this length of a paper. And that's why it's published there and not in, say, PhysRev Letters or something like that. There is also a paper by Merlin and co-workers just a few months, published a few months before that, sort of at the same time. But the reason this was published 2006 is mostly because Annals of Physics takes its time to publish. Okay, so what did Basco, Lehner, and Altschuler showed that if you have an isolated many electron system, so these are electrons it's a purely electronic problem. There are no phonons that they couple to. If you have an isolated many electron system with localized single particle state, so you're starting off with very large disorder, but allowing interactions in the Anderson-Hamiltonian, if you will. And if you add weak interactions, then you get a phase in which the conductivity is not only zero at zero temperature, but in fact is zero up to some temperature, critical temperature. And basically this, they said, was an insulator to metal transition at finite temperature in a purely isolated electronic system. And they interpreted this transition as an Anderson-like localization of many body wave functions in Fock space occupation. So basically in second quantized space, if you will, as opposed to first quantized real space. Now, one way to actually look whether eigenvalues are, eigenfunctions are localized or not is to actually look at eigenvalue distributions. What you find is that if you have localized eigenstates, basically eigenvalues that are very close by in energy are typically very far apart in real space. So they don't really interact with one another. So it's, the distribution is essentially Poisson. And that Poisson is distribution. This is the distribution of nearest neighbor eigenvalue spacings. And there is a curve there, which is the Poisson curve. And then there are some dots, which is basically a numerical simulation of, I believe, 100 by 100 matrices, okay? Done by my student. But if you have extended eigenstates, then of course, if the eigenvalues come close to each other, they will interact with one another and repel each other, which creates a big hole in this distribution function close to zero eigenvalue spacing. And the exact nature of that depends on whether you're talking about a real symmetric matrix, like in the case of Anderson localization, or you're talking about complex Hermitian matrix or a matrix which is more complicated than that. And you, in those terms, this is actually these various ensembles were studied by Wigner and by Dyson many decades ago. And for Wigner had a surmise saying, depending on whether it was real symmetric or complex Hermitian or a symplectic matrix, and those were the surmises based on a 2x2 solution or solution with two sides. And the dotted lines are actual numerical results for 100 sides. Okay, so the 2x2 does pretty well. And it certainly gets the right answer at small spacings, because it's basically two eigenvalues that are, and two eigenfunctions that are interacting with each other, with all the other eigenfunctions being further away.
There's a proof of the Wigner's distribution for large n, right?
Yeah, they do exist. This is very, I'm just trying to show that the 2x2 already is giving a pretty good answer compared to what you get in reality. Now, in 2010, David Hughes and Arijit Pal actually tried to use this to study many-body localization. I should point out that you can use this kind of statistics to study any problem. You can study whether you're studying single particle localization or you're studying many-body localization. This part is pretty much the same. Of course, the many-body matrix is a lot more complicated than the single particle matrix. That's the only difference. Okay. And what they studied was a spin-half chain with a random field. So this is an exchange interaction between nearest neighbors in a I and I+1 on a chain with exchange J. And then you have a Z field, field that couples to the Z component of the spin, that is random, okay? And it's uniformly distributed between minus H and plus H. And J is taken to be 1. That's the energy scale in the problem. And they started looking at the scaling, not of the eigenvalue splitting, but basically they looked at three splittings, okay, 2 splittings, 3 eigenvalues. Okay, if you have eigenvalues epsilon I plus 1, epsilon I minus 1, then epsilon I minus epsilon I minus 1 you call delta I, and epsilon I plus 1 minus epsilon I you call delta I plus 1. So those are the 2 splittings. And then you take the ratio of the minimum of those 2 over the maximum of those 2. And it turns out that this number is different for Poisson distribution and for Gaussian orthogonal ensemble. And it goes from somewhere around 0.53 for a Gaussian orthogonal ensemble to about 0.39 something for Poisson. And then they did it for different sizes of spin chains. And here are the sizes that are shown here, right there. It's going from 8 to 16 spins. And they find that these curves all transition from the Gaussian orthogonal ensemble value to the Poisson value. And they seem to cross at an H value somewhere around 3.5 or so. They don't do a perfect job, but that was the best that they could do. And therefore, they interpreted that as a transition from an extended regime to a localized regime. And this is the case of 1 dimension. Now, I should, in honesty, there's been 13 years since they wrote their paper, and a lot has happened since then. We do know that there is a fairly iron-tight proof, mathematical proof of the transition in 1-dimensional system, in particular, this particular model. On the other hand, that doesn't, what that shows is that you do have many body localized states at large enough H. But the belief now is that that really happens at H of order 30 or 40 or something like that. And that this, this crossing point is mostly because these sample sizes are very small. And then slowly the thing will drift off. And there is now a belief. Well, I don't know to what extent that number is even reliable, to be very honest. What I would say is that we have a mathematical proof for large enough H, it is going to be many body localized. But where the transition takes place, I would say is still up for grabs. I mean, what they know for sure is that this is not the right answer for large sizes. Okay, and it seems to be partly also because there's an intermediate behavior where you have many body localized like behavior because the dynamics is extremely slow, glassy dynamics, and I'll show you that. And the true transition probably happens at much larger. That is the current belief that I've heard from David Hughes and also Vedika Khemani. Okay, so I trust that they are doing the best job that they can as far as the numerics is concerned. So I want to put that caveat right up front. We are going to study the same thing in the quantum Hall context. And so the transition we are going to be looking at is going to be this one. We are not going to worry about things like rare fluctuation effects. In fact, we deliberately try to avoid rare fluctuation effects in our models, suppress them so that that physics doesn't come hitting you right in front. So the question basically we are going to try and address is there a really some kind of a strong quantitative change in behavior as you increase disorder? So that's the question that we will address, or that's how our results should be interpreted. Yeah. Maybe at this point, I should also give my 2 cents worth in this whole debate. You know, when you're talking about something where, say, the time scales go to being 10 orders of magnitude larger than the microscopic time scale, then it's a little bit of a maybe tautology saying that 10 to the 10 is not infinity. Okay. Yes, it's not strictly infinity. There is not a strict phase transition, but for all intents and purposes, it behaves like a phase transition. So that's the difference between structural glasses and spin glasses, for example. One of the reasons why people started studying spin glass models was because in those models there, you can actually show that there is a transition, a genuine thermodynamic transition. This of course, classical models. The transition is as a function of temperature. These are transitions as a function of disorder. They're quantum transitions in some sense. But I should mention that these eigenvalue spacings are not eigenvalues at the bottom of the band. They're eigenvalues in the middle of the band. So this is not a 0 temperature transition. This is actually an infinite temperature transition. You're basically taking, trying to figure out whether the statistics behaves like a localized, does it behave like a localized system all over its spectrum, or does it not? So that is another point that needs to be emphasized when studying many-body localization. So with that introduction to many-body localization, let me then remind you again about the quantum Hall regime. This is 2-dimensional electron gas subject to a perpendicular magnetic field. And if you have a sample that's clean but not too clean, you get plateaus in the Hall resistance and peaks in the diagonal resistance corresponding to transitions from one Landau level to the other, the so-called plateau transitions. We went through that in the last lecture. Now, when you make the sample much purer, so the other sample there probably had a mobility of about 40,000. And this is a sample that has a mobility of 10 million or more. And what you find is you get a lot more plateaus. Those plateaus don't correspond to integer filling of the Landau levels, but fractional fillings, rational fractional fillings. And we typically with odd denominators. And whenever there's these odd denominators, you find that you get the longitudinal resistance going to 0. So here is, for example, 1/3, and there is 2/5 there. And they're here, et cetera, et cetera. And you get a lot more fine structure. So what this is showing is that there are not just plateaus corresponding to integer filling of the quantum of the Landau levels, but rational fractional fillings of the Landau levels. And you have gapped states, which is why you have diagonal resistance going to 0 and quantized Hall resistance. There are also, as I pointed out, some even denominator fractions where you can get similar behavior. Actually, this 3/2, for example, is supposed to, the 5/2 that's written here is supposed to go to 0, but it doesn't in this sample because it's not cold enough. This is all very well understood in terms of the Laughlin sequence, which is nu over odd integers, 2p + 1, so 1/3, 1/5, 1/7. Those were described by Laughlin. And then Jane came with the idea of adding fluxes to electrons and making them composite fermions. And using that kind of a picture, we can then understand a whole other set of fractions. And I would say about 95% of the fractions that are seen are understood in terms of the Jane sequence. So there is definitely, it smells right to anybody who doesn't even understand the total physics of the Jane picture. So my experimental colleague, Mansoor Shayagan, from whom I've basically borrowed this slide or swiped the slide, if you will. He likes to show that just with one sweep of the magnetic field, you get all these different phases, whether they are integer quantum Hall effect or fractional quantum Hall effect, where he's trying to show the Laughlin wave function, which is liquid-like, not quite the Wigner crystal-like result, which happens at very, very low filling, below 1/5. Then the whole idea of composite fermions, topological excitations like skyrmions, charge density wave phases like striped phases and all that. All of that is seen just by changing the magnetic field, which makes anybody doing material science really envious, because in material science you have to normally make either a ternary or a quaternary alloy and put a magnetic field and put pressure and all kinds of stuff in order to get such a rich phase diagram. And even then, it does not have the richness that this one has, because this one has topological phases, it has fractionized excitations, abelian and non-abelian statistics, and all interesting phenomena which are not in there in normal cook and bake alloys. Okay. So one of the things we wanted to do was, how do you understand the fractional quantum Hall conductance in terms of topological quantum numbers? In the last lecture, I showed you that when you perform an integral over boundary condition space for single electron problem, you get integers, the Chern integers. Now, you can similarly define Chern numbers for many body eigenstates. Okay, but how do you get fractions out of it? And so that's one of the things I want to just briefly go over. And then I will talk about what happens when you disorder such a fractional quantum Hall phase, and how do you get it to be an insulator without topological properties. Okay, so the model is basically you have since we have projected everything into the lowest Landau level, so there's no kinetic energy. There is a random potential, which is this term right here, and then there is the Coulomb interaction between the electrons. Oh, sorry, the other way around. This is the random potential here, and that's the Coulomb interaction. V of Q, which is given there, it is just 2 pi E squared over the dielectric constant over Q. This is in 2 dimensions, times actually a form factor because of the fact that the wave functions are all in the lowest Landau level. So that multiplies the normal Q, V of Q for 2-dimensional Coulomb interactions. So, and again, as before, we use random white noise potential, okay? And we try and calculate the eigenstates for every random configuration for up to 8 electrons. And we thread the 24 flux quanta through the sample, so it's at 1/3 filling. Okay. Now this is a many body problem, so of course the size of the matrix you have to do is much larger. It's not just 8 eigenstates, single particle eigenstates, or 24 single particle eigenstates. It's some 700,000+ many body eigenstates. And what we do is we basically use the Landshaw's method, which is used for sparse matrices to get the lowest few eigenstates out. Okay. That's the numerical technique used, and it works very well. That's not a problem. And what you see is that what is expected, this is all done on a torus geometry, that is periodic boundary conditions. Okay. Then one can show that when you have 1/3 filling, you actually have 3 degenerate ground states. Okay. But as soon as you put on a little bit of disorder, this degeneracy vanishes because these 3 wave functions are different. They respond differently to the disorder and they split. You can actually show the splitting depends exponentially on the size of the system. And that's being shown right here, that as you make your system large, the splitting actually goes down. And so in the thermodynamic limit, there is a degeneracy. It's just not there in a finite size system. So the next question is, what happens, how do you understand the 1/3 conductivity? The reason is that basically, when you actually calculate the Chern number of these three states here, okay, what you find is that one of them has Chern number 1 and the other two have Chern number 0. So that one is shared in 3 eigenstates, and the way to understand the 1/3 conductivity is to say that the ground state manifold carries 1/3 per eigenstate. And so that's how you understand the fact that this is a 1/3 quantized Hall effect. And when you put in some amount of disorder, what you find is you can ask yourself the question, what's the probability of having, of course, a given sample may not have this exactly one Chern number, right? That is one with +1 and the other two with zeros. Well, if you look at that, what you find is in this ground state manifold, you find almost 100% of the samples have that. On the other hand, if you look at the excited state, you find that there are some probability of having a 0 Chern numbers state within the manifold of 3. There is a possibility of having 2 sometimes 3. These are all, it all depends on the disorder potential and also this exact configuration of the potential. So the way we understand this transition that is happening from a fractional quantum Hall state, in which case the ground state is given by this manifold, is that these different excited state energies actually go down in energy as the disorder is increased. And so there is a level crossing. And at very large disorder, it turns out that if you look at the lowest 3 eigenstates, they are all 3 with Chern number equal to 0. So that is basically the transition from a topological state to a non-topological Anderson insulator state. There's some other details, which is that, of course, if you look at the gap between this, while it is still in the topological state, there is a finite gap, and you can actually measure that gap numerically, and you can compare it to experiment, which measures the transport gap, what we call the mobility gap. On the other hand, there's also a spectral gap, which is just the gap between the lowest manifold and the next manifold. And therefore, that is a different quantity. That's not measured in experiment because experiments are only probing the transport. They're only probing conductivity. So rather than boring you with this details, which you can, if you're interested, you can look at I think I have the references at some point. But if not, I can give it to you. That's not an issue. But what you find is that you get both the spectral gap and the mobility gap going to 0 as a function of disorder. And what I want you to see is this particular curve where the green line is the experimental data and the red points are our best fit to the experimental data. Because we have to realize that the actual sample is finite width. Theoretically, we do the calculation for point impure, 0 thickness, but then we extended it to have finite thickness also. Because the wave function is different if you have a finite thickness layer of electrons. Okay, and we can get good fit to the experimental mobility gap, and we can sort of get roughly the right point of the transition. Okay, but this was a lot of work. We had to actually find the Chern numbers of each of the many body states, and then try and look at how eventually the lowest manifold is has no topological character. And so it took a lot of numerical effort to try and get this done. So I also want to point out something which does not use topological quantum numbers, but uses a different property. And that's quantum entanglement. And since a lot of people are interested in quantum entanglement, here's a case where we actually can predict something using quantum entanglement or entanglement entropy. So this is done with Zhao Liu, who was my postdoc about 5-7 years ago. And he's now a faculty member at Zhejiang University in Hangzhou. And what we did was we actually, again, did the same, took the same geometry, n electrons with periodic boundary condition that is on a torus, because we have periodic boundary conditions in both directions. And we, for simplicity, rather than taking, we were here not interested in trying to match the experiment. We were more interested in trying to locate the transition well and find out critical exponents if we could. And so we just took the Haldane pseudo-potential interaction. That is, Haldane showed that you can write down the interaction in terms of pseudo-potentials with different angular momenta. In this case, V1 is the only one that is needed for 1/3 state. We also studied the transition from other Laughlin states to the Anderson insulator, but the best data are for the 1/3 state because it has the biggest gap. And so the length scales involved are small and the sizes we can do are small. In the other case, we were only able to go up to 6 electrons. Here we went up to 10 actually. I'll show data up to 9. In the final published version, we were able to get data for 10 electrons also. So of course, again, here ground state has a 3-fold degeneracy. When your disorder is non-zero, we have to focus on that manifold. So when we are going to try and talk about the ground state entropy, von Neumann entropy, we have to include all 3 states, not just one. That's the crucial requirement in trying to get this thing done, okay? And what we do is we basically divide the system up into—
Hello? Ravin, I had a confusion. Hello, can you hear me?
Yes, I can hear you.
Yeah, no, because if you're working in a torus geometry,
right?
How do you get the angular momentum pseudo-potential interactions? I mean, don't you need for that? Isn't that don't you need a circular geometry for that?
No, you can do it in basically.
These are analogs of.
And yeah, exactly. And the point is that you have to, the interaction is actually on the plane. We have just the torus is only put for the boundary, right? And whereas this interaction is between 2 electrons that are typically much smaller distance than the.
I see. Okay, so you're sort of okay. All right. Okay. Fine.
So so the crucial part again here, which we got from the Chern numbers, is that we have to look at the 3-fold degenerate manifold or pseudo degenerate manifold, let's put it that way. And so when we are calculating the reduced density matrix by tracing over one part of the system, so if this is one part is A and the other part is B, we trace over one of them and we get density matrix, and then we have to look at its eigenvalues, and from the eigenvalues we can get the von Neumann entropy, and we look at the disorder average von Neumann entropy in this case. But we are, again, it's not just the ground state that we're looking at. We're looking at 3 states, and we have to average over those 3 states. They are calculated here. There is no calculation. We don't have to do any boundary condition averaging or anything like this in this calculation. So the numerical effort in doing this is much less. So instead of having to cover the entire boundary conditions angles, we don't have to. I mean, you can reduce the problem rather than doing a surface integral over the entire boundary condition space. You can do a line integral along the edge using Stokes' theorem, but you still have to do an integral, which is extra work. Here, we just take periodic boundary conditions and do it. We don't have to, for the entanglement, right?
There, yeah. Some numbers you would have to do at least a line integral.
At least a line integral. Yeah, so it's much more work. Okay. So we calculated the disorder average entanglement entropy, and what do we expect? So one expects that this will exhibit an area law in the topological phase as well as in the insulating phase. But in the topological phase, there will be a subleading term that is constant. So we tried to check that. We looked at zero disorder, very small disorder, some intermediate disorder. Infinite disorder, of course, means that we can forget about electron-electron interactions. It's a non-interacting problem. And because W is infinite and the electron interactions are finite, so we can do the mapping. And what we find in all cases that it does look linear in length. That is, it's the area of the cut in this case is perimeter. So therefore, that is goes the square root of the size of the system. Okay, so that seems to work out in both phases. So now we want to see what happens. Does something happen at the transition? And so I'm below 8. No, this is only because, well, we wanted to show it for large size. Okay, that is the, that's what you expect in the large limit. So below that, there might be corrections, actually. So here is what the entanglement entropy looks like as a function of disorder for different sizes, from 4 electrons to 9 electrons. And we average 20,000 samples up to 7, and then 8 and 9, which are take the most time, we average 5,200 samples respectively. Okay, so you will see the 9 has some error bars. You can already see the curve is not perfectly smooth. But hopefully,
This is at a particular length.
no, this is for half cut.
Half cut.
Yes, it's for exactly, we're just looking at, we're dividing the system into 2 and calculating the entanglement entropy. And so what happens is, it does look like it is getting a little, it seems to have a slope that is slightly increasing with size, but this is not a very good way to look at it. What we did was, you can actually look at the derivative of the average S with respect to W much more accurately. The way you can do it as accurately as you can get this, what you do is you take a given sample, which is near, say near this, where I'm showing you this line. Actually, it's the next slide that's going to justify putting a line there. That's where we think the transition is taking place. And what you can do is you can calculate the entropy for any size for this value of W, and then you take the same sample, increase its W value for all the white noise by 1% or actually 0.1%, and take the derivative. Because you have used exactly the same white noise, just amplified, there is no noise in that difference. If you had taken some completely random other white noise, there would be noise due to the fact that you are using 2 different samples with the right statistical property, but not exactly the same. So you actually take the derivative for each sample and then average. And then you get a very, very, very nice and reliable and
Setting a scale of the potential and making that.
with respect to the scale of the potential, that's it. Okay, and that's the data when you take the derivative. for 4, 5, 6, 7, 8, and 9. So this is DSDW average. Okay.
Why should this be?
Okay, well, I don't know, I haven't done the mathematics for this one, but I can try and draw an analogy and try and convince you that it is something that's worth looking at a transition, okay? In a thermal transition, the specific heat is the derivative of the entropy with respect to temperature. So we are arguing that in a quantum transition, the derivative of the entanglement entropy with respect to the tuning parameter, W, plays a similar role. So one should look at these curves and think of them as specific heat curves. And
That then you should have done the other thing, just taken another set of samples at a different value, done an average, and because that is already derivative with respect to the average. Also.
right. If we had enough accuracy, we would have done that. This is what we can do. Okay, because if we don't keep the same ensemble and just change, then we have just too much noise, and that's a then we'd have to take quite a big. Here we can do 0.1% change. There we would have to probably take 5% or 10%, and then that'll round out.
So what happens to variance?
Don't know. I haven't looked at that.
In MBL at least,
Right.
The variances of entanglement and that has some connection.
That may well be, okay. So what we found, I mean, I was basically looked at that and I said that if there's anything going on there, it's in the derivative. It's not in the function itself. Function itself, yes, it may be going to a infinite slope at the transition, but we are very far away from that.
What is this transition?
So this is a transition from the 1/3 topological phase to an Anderson localized ground state. It's a ground state transition. It has nothing to do with many body localization. But it is an interesting phase transition for the interacting system.
But if you computed your S, which was linear in L,
Right.
would you fit a beta and then try to plot beta?
We haven't done that, no. Yeah. Right. With that, yeah. But that would require us to extrapolate to L equal to 0, which is
You have a reasonable linear state.
right.
What a very small range of
Right, yeah. I suspect we can, but my guess is that since Zhao did not do that, he was not very happy. I mean, then there's some error bars in all these points. And so therefore, and if you're, and this is, you're extrapolating it 3 times the size of this region. So then the error.
This was why I was asking
Yeah.
you to do smaller errors.
Yeah,
Then you
right.
extrapolate it.
Yeah, of course. But then there might be some finite size effects. So, the problem was this particular transition from a fractional quantum Hall ground state to a topology, to an Anderson insulator. There is no other group that has ever studied it. We were the only ones that studied it using Chern numbers. And this seemed like a simpler way of studying it. And sure enough, now if we look at this, it looks like the peak is growing in size. I mean, it's a negative peak, but that's a separate issue because the entropy is actually decreasing. So there's one thing more that we can do, okay? If we believe that DSDW is the right thing to look at, and it scales, and it's a second order phase transition characterized by a long length scale with a diverging length scale going with an exponent nu, then you could do finite size scaling. So entropy would look, since it's linear in L at large L, so we're trying to do the large L part of we would expect that near the transition should be L times some function of L to the 1 over nu times W minus WC. This is nothing but some other function of L over C, where C goes like W minus WC to the minus nu, okay? So I can rewrite that as L to the 1 over nu times W minus WC. Now,
Sorry, I maybe missed this. Why am I not allowed to write S proportional to L to some power times?
because in the both phases we are having L.
But at the critical point, it can have a different dimension. And in principle, I would do it as L to power something and then adjust the scaling function so that in each of the phases.
That, right, maybe that, we didn't do that. We kept it as L and tried to see what we get. Now, of course, it's certainly possible that you can, so there are two things. You can extract whether this is something else. If you were going to say that, then when you take ds dw, okay, you extract out 1 over 2 nu as a result of the derivative. And so it's the function of n to the 1 over nu w minus wc, but with a different exponent in n. So you can look at both the prefactor, this one right here, and the scaling function and see if what you said there was an extra power there, then they would not match. Okay, so let's see whether they do or they don't. All right. So the first thing we noticed was we got the height of the goes as n to the 1.35. So that 0.35 or so this must be matched with 1/2 plus 1 over 2 nu. All right. How good? Could be 5% at least. Okay, I'm not going to claim that. I mean, he has written 4 digits in his fit. Of course, I don't take that seriously. Yeah, I would say that probably 2%, 5%. That is a little bit on the, because there is clear deviation from the line. There are error bars. Okay. The other thing that we can do is taking the new value that we get from here, we can then scale the data versus n to the 1 over nu divided by w minus wc. And that's the scaling we get. So we have taken out the prefactor. We've scaled the height to be the same. And we have changed the x-axis by n to the 1 over 2 nu for the 2 nu that we get from here. And that's what we get. And I would say it's reasonable. It's not fantastic, but the one that's really out of, that doesn't scale well is the smallest size, and that's what one would expect. N equals 4 is very small, but 5, 6, 7, 8, 9 seem to be reasonably scaling. So at least it's consistent. Right. So the point I'm trying to make here is that we went from a situation where there was only one calculation to see the transition and locate it roughly, to a situation where we feel this is showing the transition very, very clearly, and is also giving an exponent. I should warn you up front that this exponent violates the Harris criteria. But most quantum phase transition in disordered systems seem to do that with interacting systems. And that may be just a small size effect, that these are effective exponents, they are not the true asymptotic exponents. So that's all I want to say about the transition from the topological state to the Anderson insulator. It's a ground state transition.
So Anderson insulator does not have the topological tau.
No, it doesn't.
They expect beta to go to 0.
Right, exactly. So when everybody was doing many-body localization, we naturally asked the question, do you have many-body localization in the quantum Hall regime? Okay. And will the answer depend on which of the many fractional quantum Hall phases that we start in? And I'm going to give you the answers right up front, because that way you can sort of follow the logic of the rest of the slides without, First of all, what we find is that topology really interferes with many-body localization. If you think rare fluctuations cause many-body localization to go away in higher dimensions, this is a two-dimensional system, by the way. So it is the only two-dimensional system that I know of where a lot of work has been done about many-body localization. But we find very clearly that depending on whether the system is topological or non-topological, the characteristic as a function of disorder are very, very different. And I'll show you that. And the second thing that I want to point out is the MBL physics, the physics of localization, happens at very large disorder. And therefore, all the fractional quantum Hall gaps have disappeared at that kind of disorder. So it doesn't really matter whether you start with 1/3 or you start with 1/2 or 2/3 or some irrational filling or whatever have you. The MBL physics has nothing to do with the really rich fractional quantum Hall physics at zero disorder. Sure.
So non-interacting systems.
Yeah.
If there is a disorder-driven transition from a topology that's accompanied by some levitation of the delocalized.
Right.
And is there something? I don't know how to interpret.
How to interpret? Okay, in fact, my interpretation is that we are looking within a Landau level, right? I mean, our physics is all within a Landau level. So if I take only one Landau level as my Hilbert space, even for the non-interacting problem, nothing happens. The critical point is at the middle of the band, and it stays like that. Doesn't matter how much disorder you do, because the disorder is just a scale parameter. It is not it doesn't change the physics at all. So in fact, one of the results is, anyone who thinks about the non-interacting problem will say that if you have a non-topological band like an Anderson, tight binding band, and then you disorder it, everything becomes disordered. Whereas in a Landau level, there's always a critical energy, no matter how high the disorder is, until the disorder becomes so large that it's larger than the Landau band, splitting of Landau levels, and then there may be levitation. So we are nowhere near there. We're going to do everything within one Landau level. So again,
so you think of levitation of all the extended states of different Landau levels.
Right.
So are you saying that they rigidly levitate and by the localized space that you get is a single localized space when all of them are also
that certainly for the non-interacting problem, that seems to be true. But in a non-interacting problem, the case of free electrons is a singular point. If you start with tight binding band, what you'll find is that the total churn is 0, and you have a whole bunch of churn 1 bands, and then you have a central band with a very large negative churn number. And what is actually seen is that negative churn number band comes screaming down and starts canceling out all the churn. So there is just a cancellation of churn numbers, basically, that takes place. Now, how do you map that onto the free electron case, where basically from 0 energy to infinity, you only have half the band. The other half is on the other side of infinity, if you will.
One can conceive of situations where some of these levels are left behind and others are left with infinity. That localized state is different from the garden variety.
Yeah, of course it would be, but I don't think that the numeric supports that. Numeric supports that one by one everyone goes, and for large enough disorder, these states are not there anymore. Okay. So I just wanted to again say that we are again going to look at eigenvalue splittings and statistics of eigenvalue splittings, and in particular this ratio right here, maximum a minimum to maximum of the gaps, just like Paul and Hughes did, okay? So what we have done, and this is work done with Scott Geretz and myself first, we studied just the lowest Landau level. And we added a Haldane pseudopotential V1, white noise disorder potential, solved the many body problem for small finite size with square 2D sheets with periodic boundary condition, that is the torus geometry, and level statistics of many body eigenvalues. Okay. And looked in particular at this ratio, the minimum splitting to the maximum of 2 consecutive splittings. Okay. And one expects that for GUE, you should get about 0.6, whereas for Poisson, it's a little lower, below 0.39. Okay. And qualitatively for students, it's one can understand why this number is smaller. This number here is smaller is because eigenvalues don't repel. So the minimum, maximum can be larger and the minimum can be smaller. And so that ratio can be smaller. Whereas in this case, there's a lot of repulsion between eigenvalues. And so the ratio of the 2 gaps is closer to 1. So if you look at the results for the lowest Landau level, we again look at R. This is the plot that I showed you for the one-dimensional spin chain. Here again, for small w, you see that the R value is pretty close to 0.6. And for large w, it goes to 0.38 something, 3, okay? But notice that the w that I'm plotting is on a log scale, okay? It's 1 at the bottom on the left-hand side and 10 to the 4 on the right-hand side. So that's already telling you that something is very crazy about it. It's not on a linear scale at all, okay? The other thing, so we said we don't know whether this is really a transition taking place or not, but let's presume that the halfway point is sort of telling you when it's going over for any finite size system from a GUE type state to a Poisson state. Now, I'm not claiming that this is the value at the critical point, but it's just a characteristic of. No, they don't cross as far as we can tell. It's not only that, if you look at this midway point, it's marching to larger W as size goes. And we are talking about sizes from 3 to 6. And that midway point has gone by more than an order of magnitude in W. Okay, so if I plot that, if I call that critical W, it's of course not the place where a transition takes place, but it's a characteristic W at which it crosses over from one to the other. Then this W seems to, the critical W seems to go from L to the 4 to L to the 5. And we have done it for 1/3 and halfway in the band, 1/4 way in the band. We've also tried it for other fillings, and it's really marching like crazy. So this is basically saying this is consistent with there being no many-body localization in the thermodynamic limit. Basically, this entire curve will just go like that, and then maybe, come down for very large size. And if you go to even larger size, it'll be exponentially larger W is what is needed. So it is consistent with the result that there is no many-body localization in the thermodynamic limit. Now, there is actually an argument due to Nandkishore and Potter, which says that there should be no many-body localization in a Landau band or in one Landau level. And the argument is they started with a locator expansion, just like Anderson did. And the idea is that if you have interactions, then the hopping term gets enhanced because of the interaction. Because of the fact that there is a critical, there are very extended states that are tending to diverge at the center of the band get mixed in. And so they estimate that the hopping goes as a power law in R, okay? With negative power law in R with an exponent that's d plus 1 over nu over 2. And he says when that hopping exceeds the eigenvalue spacing, which goes as r to the minus d, then one should, if that is what happens at in the large distance limit, then we have to decide which one is dominant. And so what it says, if nu is greater than 1 over d, then at large r, this hopping is much larger than the eigenvalue spacing, and so you don't have localized states anymore. The locator expansion fails to converge. Okay. And you can use the same argument for some finite size L. We just say compare T at length scale L to the delta, the spacing at length scale L. And what you find is that W over V should go as L to the D minus 1 over nu to the quarter. Now, if I put in the fact that this is a two-dimensional system, and we know that the exponent for the localization length at the center of the Landau band is around 2.5, it gives L to the 0.4. That's a very, very weak dependence on L. We found L to the 4 or L to the 5. So we are saying that there's some additional stuff going on, at least at the length scales we are probing, beyond what Nandkishore and Potter. We are not saying that their argument is wrong in the large size limit, but at lower sizes, it does seems like there's a much greater dependence on size. Okay. So that is one thing that has not been analytically understood.
In this argument, don't do anything to renormalize the denominator. They
Yeah.
basically end up with the possibility of having just bare resonances,
Right.
which we know will not be there if one does.
Yeah, it goes to higher order.
Yeah.
Well, since their results don't match numerics, I would say that there's definitely something that needs to be done. It does need to be changed. I mean, either their process that they are talking about is not the right thing that's happening. There are other things happening which are dominating, or else the way they did it may have some flaws in it. And that's certainly something that should be looked at. So one of the questions, of course, you can ask is, the fact that we don't have many body localization in a Landau band, what's the reason for that? Is it the fact that there's topology in the Landau band, or is it the fact that it's two-dimensional as opposed to one-dimensional spin chain where people found a transition? Okay. And so what we did was something interesting. We took a Landau level and we added a Hofstadter periodic potential to it. And we added the periodic potential with sufficient number of Fourier components that the Landau band split into two bands. Okay, Landau level split into two bands. There's no disorder yet. We split it into two bands. And these two bands have a bandwidth that are comparable. In these units, they are 1. And the band gap is 8700 in these same units. So basically what we've done is we've taken the Landau level, split it into two dispersing bands, very weakly dispersing bands with a large band gap. So now we say that, well, let's look at each band separately and try and see whether they can be many-body localized or not. One of them has Chern number 1, the other one has Chern number 0. Of course, the sum of the Chern numbers has to be 1 because that's what the Landau level has. So if you look at the two bands, they look roughly the same. They're not identically dispersing, but the width is similar. The number of wiggles are similar.
So what do you know about the wave flux density?
We don't know. I don't know what it is. I mean, the potential has peaks and valleys quite a bit. It goes from plus 40 to minus 40 in these units. So that's, but the bands are flat order 1. So bands are order and a half magnitude less than the potential fluctuations. And the band gap is an order and a half larger than the potential.
I think that once you allow the bands bandwidth
Right,
and the eddy flux density
right.
did not be correlated in the sense that the eddy flux density can have a very anisotropic distribution even for an almost flat band.
I mean, when you say anisotropic, it still has to have square symmetry because the potential is square. Yeah. Yeah, it may not be uniform. It may not be, certainly. We didn't look at that. Okay. So we looked at the problem for the Chern 0 band and the Chern 1 band, and we couldn't, you'll see in a moment why two-dimensional scaling is very hard to do in this case. But what we did do was a one-dimensional scaling, fixed width, keep on increasing the length, and see how this R average goes from the GUE value to the Poisson value. And what it says is that the Chern 0 band seems to show a transition in this one-dimensional geometry. Okay, so this is really one-dimensional rather than two-dimensional problem. At a disorder that is at least an order of magnitude less than the Chern 1 band, even though the two bands are pretty similar looking. Okay, and the crossing for the Chern 1 band is, you could say is yes, it's there or not. But one of the other things we did was we tried to see whether the halfway point, how that varied for different sizes. Okay, and what you see invariably is for the Chern 1 band, the halfway point is increasing quite dramatically with the size of the system. It's not going at L to the 4th anymore. It's not quite that dramatic. But whereas for the Chern 0 band, it seems to be having the opposite curvature. So it looks like it's going to a finite value. I mean, we cannot say that that's definite. I mean, I've done enough numerics to know that these things can turn out and bite you if you make too many. But certainly the curvature of the two curves is opposite to each other. So I would say it looks like the Chern 0 band many body localizes. Chern 1 band, does it localize or not? One can't say.
What was the band gap on this scale? Much larger?
The band gap was 8,000. So it's 8 times 10 to the 3. Right. So it's way far. So we can assume that the other band is not affecting anything. Yeah. Right. We tried doing two-dimensional scaling, okay? There is a problem. You have to satisfy the constraint that the number of electrons is integer. You have to satisfy the constraint that the lattice size on each direction is integer. And therefore, you can't satisfy the constraint that the density of electrons is fixed. So you have to start doing interpolation. So that's where the problem starts. It tells you immediately that finite size scaling for a two-dimensional system with lattice geometry is a real problem. It's not easy to do, okay? And to the extent that we can do it, again, we sort of relied on the halfway point rather than on crossings. You can see that there are crossings are happening, but they are very size dependent. And what you again see is the same story, that for the Chern, unfortunately, I think the color coding is wrong, opposite in this case, but this is the Chern 0 band and that's the Chern 1 band as a function of size. And so again, the same story, that it's saying that maybe the Chern 0 band has a MBL, but certainly the Chern 1 band doesn't. And I won't even trust that Chern 0 band having a finite MBL, because if you look at the crossing for the Chern 0 band, you see that it's moving all over and it's not staying put. This is only the WC defined as when R goes to 0.5. That is halfway between 0.6 and 0.4. So that's one of the problems. So I came up with a solution for that, okay? And the solution is that you, instead of trying to form two bands, Chern 0 band and a Chern 1 band, subbands that are with a periodic potential, you instead put delta function impurities in the Landau level. If you do delta function impurity, one single delta function impurity in a lambda level, it pulls out one bound state. That's something was shown by Prange in 1981. He was trying to explain the integer quantum Hall effect by showing that if you pull out one impurity, one state, it doesn't change the Hall conductance at all. That was later generalized by Brezin, Gross, and Itzekson 2 years later, where they said that if you have a whole finite set of impurities which have delta function potentials, then you pull out as many bound states as there are potentials. And so long as that number is less than the number of flux quanta, your Landau level still has some eigenstates. Basically, those eigenstates are the ones that have zeros at this impurity. Now that you've learned about thinking about Landau level wave functions in terms of their zeros, you can understand that by putting a zero of the Landau level wave function at the impurity, the impurity doesn't perturb it. So if you have n delta impurities and n phi flux quanta, n phi minus n delta states remain at the unperturbed energy level because they can put their zeros at the impurities. And then there are some others left which cannot put zeros on the impurities, and therefore they form an impurity band. So that's what we did. We put in a bunch of delta function impurities and pulled out some states and made an impurity band. Okay. Now this impurity band has Chern number 0 because the Chern number stays with the extended states in the Landau level. And so now we have the Landau level, in fact, looks very much like an unperturbed Landau level because we are forming an impurity band with less than, only a few % of the states in the Landau level. And then we try and, these impurities are randomly configured. So then if you take an ensemble average for a fixed density, you can choose any number of electrons. And since this is in continuum, the density is fixed. So you can do different sizes. That just determines how many impurities you have to put in. And the impurities are distributed randomly. And we didn't allow it to be totally Poisson distributed. We put a little bit of a hard sphere constraint. Because we didn't want some rare fluctuation, configuration to dominate our results. So this is one way of trying to get rid of rare configuration issues, at least at the scale that we are looking at. Okay, and we did exactly the same thing. Yeah.
When you say that the Landau level remains sharp,
right?
What you mean is that if the difference between the impurity band and the Landau level energy scale is delta,
right,
the width of the Landau level is 1 over delta.
No, these are exactly because the wave function, because it's a delta function impurity. If the impurity had finite width, then yes, you would be right. Because the impurity is a delta function, we can put some of the Landau level wave functions such that they have zeros at all the delta and delta impurities. They all supposed to have n phi zeros. Of the n phi zeros, n delta are at the impurities. So they remain exactly at zero.
They're smaller than the magnitude.
Right. It's not even small. I mean, of course, it needs that, but the model considered by Brezin, Gross, and Itzekson is exactly delta functions. Okay. So there is absolutely no mathematical issue. There's no magnetic length even. All right. So we tried to do that for different sizes. Now we don't have any constraint because it's a continuum model problem. The lattice size can be anything we want. And we can do it for such that the density is maintained. All right. And so now we can do 4, 5, 6, 7, 8 electrons. Okay. And look at how it works for one-dimensional scaling. Basically taking a square sample and then making it rectangular as it goes from 4 to 8. And clearly R versus W has a crossing. This is for the impurity band, by the way. Okay, so it's for the non-topological band. we definitely have a crossing in this case. If we do two-dimensional scaling, that is now we do go from square to a bigger square to a bigger square, we do have crossings, but the crossing point moves very with the W. So we cannot say whether the limit is finite or not, because we don't have enough sizes. We have n 4 to 8. But there seems to be enough movement. If you look at, the 4 one, which is this guy, it crosses here, but by the time you go to the largest one, they're crossing somewhere here. So there's a fair amount of movement of the crossing point. Unfortunately, we don't have enough data to tell for sure what is, how the systematics of the crossing point is as a function of size. And so I don't want to make a prediction whether this is going to be many-body localized or not in this sense. But what it is saying is that this is very different from the Landau level, where the curves were just never crossing. They were, moving orders of magnitude within the same sizes. And if I look at the rest of the Landau level that is left behind, because we have only taken out a few wave functions, it's going to behave like a Landau level. It's not going to behave much differently. We tried one more final thing with the lattice model. What we tried to do is we tried to build in a charge imbalance by
pinching out states into the impurity band,
right.
And then some evidence for localization in that impurity band. So wouldn't you say that that localized state with sort of measure 0 states in the Landau level, okay, is a different localized state than like if you didn't have the Landau level?
I don't know whether it will. At this stage, I'm not making any prediction, but yeah, you are taking out the localized state from a Landau level. There's no question about that. So whether there's any.
You're pinching out states and making them localized.
Yeah, we're making basically a tight binding band out of them.
Yeah, but the fact that a measure 0 number of extended states remain, okay, if you pinch too many states.
Right.
Like so that I think.
No, I mean, we are not very close to, even pinching off, 20% of the states.
Yeah.
Because if you try to pinch off too many states, okay, then what happens is that the bandwidth of this this will start tailing into the Landau level.
I see. You cannot control that with the strength of the delta function.
No, because that just sets a scale. That's all. That just right. Because the size of the wave function also depends on that. So basically, what happens is that you're stuck having a narrow impurity band made out of a small fraction of the Landau level. That's what you can do things with. And in that band, you do see many-body localization, certainly in the one-dimensional case and possibly in the two-dimensional case. So one final thing that we did for the mini bands that we had, the 2 mini bands we did, we tried to start on a state that is initial charge density has a cosine variation to it, and then try to see whether it relaxes to uniform charge density under unitary evolution. And I don't want to go into too much detail except to show you these 2 curves, which are these how much of the memory is retained. Okay, so here is the churn 0 band. What you find is that at long time, so this is all long time result for different values of W. And we find that more than 80% of the initial state is retained in the final state. I mean, we have run it for as long as we can. When we see no change, we stop. Whereas if I look at the churn 1 band, we find only 20% is retained, 20 to 30%. 70% has relaxed off. So I'm not claiming that these are, it's not 100% and 0. That's not what we see in these finite size systems. But it is actually, there's a significant difference between the Chern 1 band and the Chern 0 band. Again, as was seen for the, the R parameter. And if we sort of squint our eyes and say, well, what I'm going to do is I'm just going to take the midway point between 0 and this one and see how that varies with size, okay? So if I look at the motion of this with size here and the corresponding motion of this in the halfway point with size here, what you find is that the Chern 1 band, the motion, it moves out to very large W very quickly. Whereas the Chern 0 band has again the opposite curvature, very similar to what was seen for the, this is for the R values, and this is for the dynamics. How much memory is retained or not. So in both cases, it seems to suggest that the Chern, the bandwidth, which has a topological character, is not wanting to many-body localize. Certainly very much more resistant than a band that is has no topological character. Okay, that brings me to the final summary slides for not only this lecture, but also the previous lecture. So first of all, I want to summarize the previous lecture, which is make a case that calculation of the topological quantum number is a powerful method to study the quantum Hall regime. We saw that for the non-interacting case in Tuesday's talk, and today I showed you the result, the first results for the topological phase to Anderson insulator transition came from such studies. Okay. For the integer quantum Hall effect and non-interacting case, we saw that the critical behavior of plateau transitions and for random field all could be explained that way. We saw floating of extended states, and we could understand phase transitions in periodic and random potential, which I didn't go into more detail in these lectures. When it comes to the fractional quantum Hall effect, the topological, the ground state manifold has a degeneracy on a torus, and that's how we understand fractional plateaus. And we showed that the mobility gap and the spectral gap, the mobility gap telling you what you measure in transport, they are quantitatively different, and we can get agreement with the experimentally measured activation gap. And finally, I added that entanglement entropy seems to give an even better handle on the topological transition. These are all ground state transitions. Now I want to sort of summarize the many-body localization part of these lectures. That first of all, it's a frontier topic of research in condensed matter, and it derives its inspiration from Anderson localization, basically. But it has far-reaching consequences that were not quite envisaged 70 years ago. It comes with the destruction of eigenstate thermalization hypothesis. These quantum states don't thermalize. Instead, they retain memory of their initial state at arbitrary long times. The assumption that under quantum dynamic, unitary dynamics, you will cover all of phase space and therefore thermalize is just not borne out in this case. So in that sense, it's an extremely important result. Unfortunately, it's only been established for spin chains in transfer field spin half chains, and it's not clear that it survives higher dimensions. And most of the reasons for that seems to be rare fluctuation effects. What we have added to that is saying that if there's some topology involved, then that makes it even worse. Numerical methods are useful, but not, they face some really horrendous problems. The horrendous problem with the Hilbert space with system length size is exponential. So it makes it very, very hard to simulate anything but the small size system. And of course, you want to make that whose quantity, whose power you are taking that goes with the length of the system as small as possible. That's why everyone's doing spins, because the spins can be up and down. And that's about it. Quantum Hall is two-dimensional, so it's a little more problematic, but in some sense, because of topology, the assumption was that it is closer to one dimension than two dimensions. But you know, in terms of the work, it was certainly very much more work than spin chains.
But the fact that topology interface with localization is
Right.
also true for Anderson.
Right, of course. It is true in one for the single particle situation.
If you take a topological band insulator, it's impossible to
To-
localize the surface states.
Right, yeah, exactly. In two dimensions, that's the statement is that at the center of the band, you always have a diverging localization. That's right. So the platform of, Landau levels in two dimensions is an alternative. That's what I've tried to show. It's more hard work. The strength is that you can have a continuum model, so it's not limited to lattices, whereas spin models are limited to lattices. So once you go to higher dimensions, you're going to have the same problems with spin models as you have with lattice periodic potentials here. Whereas we don't need to do periodic potentials and get the physics out. So in some sense, if you think that you had a computer that had, 1 million times the power of the computer that we have today, it's quite possible that the quantum Hall problem will win at large distances, because you can just do arbitrary sizes in 2D, which you can't do with spin models. The results is that there's a clear effect of topology on many-body localization. Non-topological bands can be many-body localized, but topological bands really resist MBL. For one-dimensional scaling, MBL appears robust in both impurity and Hofstadter for the non-topological band. And again, the topological bands don't show the same behavior. And for two-dimensional scaling, MBL is found to occur in non-topological band, but whether it's just a finite size effect or whether it survives in the thermodynamic limit is not known. But if you have topological bands in 2D, they just really refuse to many-body localize. So that's the punchline of this lecture, I would say. So I'll stop at that point.
So before we go on to questions, let me thank Professor Bhatt on behalf of the entire TIFR system for this wonderful set of lectures. And I think that a lot of us would revisit these lectures over time to understand some of these things. And I think it's a prized addition to the online lecture series that we have within TIFR. So with that, questions from people here or online. I think we had some questions, but yeah.
Anyone online have any questions?
Yeah. Okay, doesn't seem to be the case.
Hi, Shubhro, can I ask a question?
Please, Aarti.
Hello, Professor Bhatt. Thanks a lot for very interesting lectures. So I think I missed one point in today's talk. So at some point when you were showing the derivative of the entanglement entropy as a function of disorder, the transition point seemed to be around W equal to 0.6. But then when you were looking at the level spacing ratio, it seems that the transition, you really had to go to very, very large values of disorder to get the Poissonian statistics.
Yes, that's because the first one, we were just looking at the ground state transition, the transition from the topological ground state to the non-topological ground state. Whereas when we are looking at eigenvalue statistics, we're looking at excited states. So we're looking at the typical state inside the many-body set of, not the same transition. One is mostly.
I see. So you were looking at the full spectra when you were looking at the level spacing ratio.
Right. In one case, it was just looking at the very low energy spectrum.
So have you also looked at the entanglement entropy for states in the middle of the spectrum?
No, we haven't done that. No.
Okay.
It's something that should be done, I would assume, just to see how different the eigenstates in the middle of the spectrum are compared to the ground state. I mean, as we are beginning to realize in most many body systems, ground states and low-lying excited states, there's statistics, there's splittings, their nature, all of those are very different than what happens in the middle of the many body.
Yeah, yeah.
And I think that is a very fertile subject for studying for numerics. And I would encourage young people to try and put their own stakes in that question, whatever system they're trying to. Very useful for understanding many body systems with disorder.
Okay, thank you.
Thanks. So more questions from people online? Okay, if not, let's thank Professor Bhatt once more for this set of lectures.
Thank you.
Thank you.